This is another example where it's a very common example called move, right? So move, load, these are, you should remember, these are data movement operations. They are not really doing any computation per se, but uh, ferrying data around in the processor sometimes is extremely important because you do not have a lot of resources to keep the data locally. You need to move out data to make room for new data coming in. So you need to often swap out data and swap in data, right? So lots of data juggling instructions have been provided, and move is one of them. And this instruction makes a copy of one register into another. Very humble, simple instruction, MOV. The source register RR is left unchanged, so this is very important. The reason I kind of am showing you real world examples is to help you calibrate how instructions actually look like in the real world and what kind of things are specified. See, once you are copying the content of RR into RD, right, the manual also makes sure that, or it says that RR is left unchanged. So you need to be very cautious about these operations and stating these things in the manual, right? So RR is being copied to RD, fine, RD will get the value being stored in RR, but what happens to RR, right? In a certain processor, it might affect the value, it might become 0 or it might be reset, right? But it is not the case, and that is what is mentioned here. RR is left unchanged. Okay, don't think that move is an universal instruction and it is going to work in the same way across all the ISs. That is not true. It need not be the same outcome in any processor architecture. It depends, right? And that is why you have to write this contract. This is a piece of contract that is given by the AVR architecture uh, to the software programmers. Okay, because if it is not unchanged, you might lose the value, right? And who will take care of that? Your entire logic that you have used for your program might become completely wrong, right? This is hardware, it's not your like a mathematical assignment that you think that if x is taking the value of y is not affected. That's not that, right? This is implemented in hardware, and a certain microarchitecture might have an implementation that leaves it changed. Okay, so that's just a note. So here move RD RR. So as I also did this thing, right? Move A comma B. So A is the destination register and R is the source register. So A is loaded by the contents of B. So one more thing that you need to understand is by execution of this instruction, the program counter is incremented by 1. So in our case, this program counter is pointing to an instruction, and that instruction could be having uh, whatever number of let's say 16 bits, right? And it basically goes to the next location in the memory. Okay, so it could increment the program counter by uh, a 1 here. Okay, the value is that next address. Okay, so there could be also some instructions that require more number of 16 bits, right? Not one 16-bit opcode is not sufficient. You might want to specify another full address. In that case, you might actually end up using two 16-bit opcodes, which make your entire instruction 32 bits. Okay, so in that case, PC should be updated to PC plus 2 and not PC plus 1. Right, I'm not going into that discussion. In our case, we are not going to look into this multi-word instruction. This is a one instruction is one word, right? Typically in this case is 16-bit. In Gajendra case, it is going to be 8 bits. Okay, so here also you can all come up with this sort of instructions. Let's say move R7 comma R25. Okay, so it's basically R7 is going to be loaded by the contents of R25, right? So 7 is we are going to use 5 bits. Note that here there is a flexibility. Earlier in case of LDI the flexibility was not there because it was being, the bits were being eaten up by the immediate value, which is itself 8 bits, right? In this case we have enough room. Okay, so R7 is in 5 bits, it will be 0 0 sorry 1 1 1, right? So 5 bits, this is 7, and 25 is 16 plus 9, so 1001 is 9 and 16, right? So this is 25. Now look at the weird way in which these bits are distributed in the opcode. Okay, and you can't really do anything about it. That is how the underlying implementation may be efficiently done, right? So you may think that the reason I was telling you this is weird, see, the value of R, so which is basically your 25, and this is your D, I guess. So this D is going to be 0, right? This is going to be 0 1 1 1. Now you will see that one bit of R is on the left side of D, which could be, I mean, very funny for us. Why it is the case, we don't know. But maybe this is the way, if an instruction set is organized in this way, the instruction format is organized in this way, it makes the hardware implementation simpler. Because I cannot, as I told you, make it friendly for a human user. Rather it has to be friendly such that the underlying microarchitecture is simple. Okay, and you have to design it for a lot of different instructions. It's not just move. The same instruction, the same underlying hardware is going to be used for many different instructions, right? Not just move. Okay, so there could be various decisions that are taken to make this kind of choices. So this R is now going to become 1. The rest of it is 1001 1001. Okay, so this is your R and D is in red. The rest of the bits are 0010 and this is 1. Okay, so you can see what is the machine code for this particular instruction. The machine code is going to become 0x, right? 0x is because I am using an hexadecimal notation, and then 0010 is 2, so you can always write 2. Then this is 1 1 is given, RD is 10, right? So this becomes 1110, right? Which is E, right? E, right? 1110 is 1 less than 1111, which is F, right? 1110 is E. Okay. Then we have 01111, which is 7. Then we have 1001, which is 9. So if I want to do move R7 comma R25 in the machine code, or it passes through an assembler, the assembler is going to tell that this is going to be the output or the corresponding machine code for that instruction. Okay. Similarly, you can have addition, right? Addition is not a data movement instruction. The addition is going to actually use the ALU, or the arithmetic and logical unit, and here they have clearly specified that it's first of all not going to assume any input carry. So if you think of a full adder, if it is a full adder circuit, it is going to have A, it is going to have B, it is also going to have an input carry C in, and you are going to have a sum bit, sum, and carry out. Okay, so a full adder does this, and you basically, this is a 1-bit full adder, but you can always extend this to have a 8-bit full adder, because in this particular case we are going to always add 8-bit numbers, right? Both in case of the AVR architecture as well as the simple one that we are going to study, the Gajendra 1 architecture, the adders are going to be 8 bits. Okay, so it adds two registers without the C flag. So you need to understand that in this particular instruction, C in is disregarded. Okay, carry in is not respected. So it is without the carry flag. And now why it is called a C flag? Carry, as I told you, there is no separate way to store the carry other than in the status register. A little while ago I talked about the status register, and now you can see how these things play a role. So if there was a previous carry from a previous operation, carry flag could have been set, and this operation is a it does not respect the previous carry. So we want to do a addition afresh. I don't want to influence my addition from a previous carry flag that has been set. It's a fresh addition. So I will not respect this C in, and the operation looks like this. You need to mention two registers, RD and RR, and the destination value is the destination register is RD. Okay, so that is now implicit. So you can think of this RD as a source, src underscore 1, source 1. This is src underscore 2, but this is also a destination. Okay, so this is implicitly mentioned. If you look at a program function in software, it is already written that okay, these are my input parameters and this is the return type or the return value, right? Here the destination as well as the source one are the same is only mentioned in the instruction set manual. Okay, just by looking at this you will not be able to figure it out. You have to go to the Atmel AVR instruction set manual and figure out what this add instruction means and what it does and what it affects, right? Maybe after it gets executed, I have not given the details here, but if you actually look at this instruction set architecture, this is all publicly available. You can simply type Atmega 328p AVR instruction set in Google, you will get this document, right? I have taken snapshots from that document to show you how things look like so that you can relate. Okay. Similarly, I can find out an instruction, the machine code for this, and C out could actually go to the status flag. Okay, A is your RD, right? This is your RR, and the sum is also going to go to your RD. Okay, so as you can understand, this is a part of the ALU. The full adder is going to sit inside the ALU, and ALU is going to be connected to the common bus, and any register can write to the common bus. In that way you can get the addition done. Okay, so here also I have the flexibility to choose any register out of the 32 registers. So 5 plus 5, 10 bits. I still have 6 bits more, and those 6 bits are enough to express the fact that this is addition. Okay, again if I want to do the same thing that I did last time, in the last example we did move R7 R25. Even if we do, let's say, add R7 comma R25, these are not going to change anything because there's a lot of registers that are being copied and probably added, right? So all of it is same. As you can see, there is no difference in the least significant 12 bits are the same. 1 1 RD, DD RR RR. Similarly here also 1 1 RD, DD RR RR. Okay, so only thing that is different is the 0000. So earlier it was 0010. So it was 2E79. This one will be 0E79. So 0x 0E79. Okay. So when you write a program in machine code, you have to write the program in this way. So you have to keep on writing all these strange looking numbers, and these numbers are going to be interpreted by the hardware. The hardware will understand what this 0E79 means. It will fetch this 0E79 from the memory and load it in the instruction register, and the instruction register is going to pass it on to the control, as well as there is something called instruction decoder. We are going to look at that later, and that instruction decoder will see that, oh, there is a 0 in the beginning, this means add, or it will see there is a 2 in the beginning, it is going to mean move, and based on that it is going to take specific actions. Okay. One more example with a logical operation. Typically logical operations are also done in the ALU. Here it's an AND operation. Okay, and this AND operation is not in between two registers, but a register and an immediate value. Okay, so we have already looked at LDI, right? LDI was load immediate. So this is also AND immediate. The immediate value is a 8-bit constant. Okay, so same thing, right? These 8 bits are gone, and because 8 bits are gone here, and probably these 4 bits are required to identify the AND operation, or AND I operation rather, you have to only have the flexibility of addressing 4 CPU registers. Sorry, 16 CPU registers by using 4 bits. Okay, that's why it is 16 to 31. So 4 plus 4 here plus 4 and here 4, 16 bits. What is the challenge here is the 16 bits. How much functionality you can pack inside 16 bits. That is the design part of it, right? Or if it is given to you, it is very trivial. The thing that we are kind of currently doing is trivial, right? It has been given to you that follow these things, you will basically get the machine code. There is nothing challenging, intellectually challenging to do anything of that sort, right? Rather, what is challenging is to come up with an instruction set architecture that is useful. It has to be useful, it has to be practical, right? It has to be something that programmers can use with ease. The compiler can be written in a more optimized way, right? Then only your instruction set architecture is successful, right? So what we are doing is simply looking at the instruction set architecture and trying to make sense out of it, right? Not even make sense out of it, just trying to read their description and in a very descriptive way like find out the equivalent machine code. We have not looked at the entire instruction set architecture and making any high level discussion on that. That is not something that we are doing, or even we will try to do as a part of this course, right? So here RD contains some value, and you are putting an 8-bit constant, and you want to do an AND operation of that, and write the result in the destination register, right? So I'm not going into the detail. It's very simple. Whatever bits you have in RD, so this is RD, you have some 8 bits, right? And K is also going to have this 8 bits, right? You do an AND operation, right? I'm saying this is AND, logical AND, right? Or I mean, or like rather, I like not, just to be on the safe side, I would say bitwise AND. So this is going to be ANDed, this is going to be ANDed, this is going to be ANDed, and so on. And the result is going to be again loaded in RD. Okay. So these are the like 4 examples I thought that I will give you to make you more comfortable with what instructions look like in the real world, so that you will not be kind of thinking that whatever we are learning, although is at a small scale, but it is something which can be very easily extrapolated to reality, right? Although the ISA that we are using is a more of a toy type, but as you can see that there is not much of a difference, right? Other than the scale, or maybe there is a lot of thought process that has gone in order to design the ISA. We are not putting much thought in coming up with the ISA in a very systematic way or in a tricky way to optimize something. We are just saying that 4 bits for the opcode, or 4 bits for the operation, and 4 bits for the operands, and out of those 4 bits you can support these many instructions, right? But we are not really arguing about what should be the architecture of putting the, how should the bits be placed, or what kind of instructions should be supported. Those things are not being discussed as a part of this course, but we will focus on, given the ISA, how to build the underlying microarchitecture to satisfy that ISA, right? So I will not go into any more real world examples. We will stick to our uh, CPU, right? And we are going to introduce some of the instructions that we are going to support as a part of the Gajendra 1 architecture, right? So some of them could be NOP, right? NOP means no operation actually. Sometimes we may need that. For example, if you have a loop that has a knob, right? So this is something which is very similar to a sleep operation, right? So if you want to, if you want the CPU to do nothing for, let's say, 1 second, maybe you can write a loop, right? And in a loop it does knob, and the loop executes very fast because the processor clock is very, very fast. And you can have a loop counter variable. Maybe it counts from 0 to, let's say, 16,000, right? And for every such iteration it does nothing, right? But it is going to kill time, right? So sometimes they may have uses. Halt is going to halt your program, right? Your program executes, and it stops executing anymore, because we are not going to have any operating system support as a part of this thing right now. We are going to manually start the program, and once the program is done with its execution, you have to stop the program, right? So that the program counter is not incremented anymore. So this is a halt instruction which is going to stop the program, or you can say freeze or pause the computer. Then you may have some loading and storing instructions which are called LDA, is loading the accumulator. We are going to also look at the syntax, right, in the future lectures. So LDA is loading the accumulator with a particular value stored in a certain address. Okay, so this is called LDA, load accumulator. Accumulator stands for accumulator. A is accumulator. So I will use the term accumulator and register A interchangeably. Okay, accumulator is equivalent to register A. Okay, so LDA is exact opposite of STA. STA is store accumulator, where the accumulator's value is going to be stored at a certain memory address. So if you say STA 0x50, it is going to look at the accumulator. Suppose in the accumulator it contains the value 57. So 57 is going to be written to the memory address 0x50. Okay, and the other way around for LDA. So if let's say 0x50 contains the value 37, 37 is going to be written to the accumulator. LDI is load immediate. It has nothing to do with memory. So this is a memory instruction. This is also going to deal with memory. This is immediate. Okay. There is also something called indirect. I'm not going to introduce that right now. Immediate here means that you are passing the value as a constant which is going to be loaded to the accumulator. So this is very similar to what we also had as a part of the AVR instruction set. So LDI 77 means you want to load the value 77 in the accumulator. Okay, there is a small catch here. That is why I mentioned this number 77. You need to understand that LDI 77 is not possible in our Gajendra architecture because of the limitations in the number of bits we have in the instruction. The instruction only has 8 bits, right? And the first 4 bits are already exhausted for specifying the fact that this is LDI, right? So we only have 4 remaining bits. So any constant that has to be specified cannot be more than the value 15. It has only to be only 4 bits. So I can only do LDI 0, LDI 1, dot dot dot, LDI 15, not more than that. You need to be very careful about it. So this is one restriction, our immediate shortcomings of our ISA that you can directly see. We have not put enough thought in order to create this instruction set. Of course, it is going to have limitations. Okay, so although I have space in my accumulator, I can support up to 1 byte, but I am only able to load a constant that is up to 15. The value is up to 15. Okay, that is one drawback. Then we have register transfer operations. We can have operations like move. So this move are typically register 1 to some register 2, right? And we can also have a swap, which is more of an exchange, right? If you have a register 1 and register 2, I want to swap the contents of these 2 registers. So this is, we actually have an instruction called, I think, XCHG, if I'm not mistaken. This is called exchange operation in between 2 registers, which is we are calling it swap. Okay. Then you have arithmetic operations. It could be addition, subtraction, right? These are the 2 things that we are going to support. And we are also going to have some branching instructions, which is similar to your go-to, right? Once you execute a few steps in the program and based on a certain condition, let's say if A is greater than B, go and do something, right? If A is less than equal to B, do something else, right? So to maintain some kind of the flow of your code, the way your program is executed, the structural flow could be changed, right? Based on where you want to take the control to, right? So that is done by this branching instructions. One is jump. So jump is going to also take address with it, because I have not yet mentioned the syntax for this instructions yet. Here I am introducing the kind of instructions that we are going to support. So jump is often called an unconditional jump. So I'm not checking any conditions, I'm simply jumping, right? So this is like a it could be useful in an infinite for loop, right, or an infinite while loop. So you do certain things and then jump to the beginning. Again you do certain things and then you jump to the beginning. It's like a while true we often write, right? So jump is like that. But you can also have this jump based on a certain condition. So suppose I want to write a for loop, right? Let's say for I equal to, or let's say I want to do something like this, right? While let's say n minus minus, I want to do something, right? How do I know that this loop has terminated? Because n could be initialized, let's say n equal to 100, right? And n minus minus is a subtraction operation that may take place in the ALU, and based on the result, the 0 flag could be set or unset. So it will iterate through values, right? N equal to 100, and here you can have something like JNZ. Okay, so what is the JNZ going to do? You are going to initialize n with the value of 100, then it becomes 99, then it becomes 98. At some point of time, this is going to become 0, right? If it is going to become 0, it should not jump anymore to the beginning, right? To the, again, the while statement. It is only going to jump if it is not 0. If it is 0, it is again going to continue the rest of the instructions or rest of the code. Okay, so J and Z could be a very useful instruction in our instruction set to have some loops with controls, right? I want to actually iterate for a fixed number of times, right? In that case, I can load the iterator with some count value and decrement that count value, and if it reaches the value 0, then I am done with repeating the same stuff some n number of times. Okay, one quick example I can give you is that of multiplication, because in the arithmetic operation we do not have any MUL, right? No multiplication operation. I do not have hardware in my ALU to support multiplication, right? So one thing that we could do is that we can do repeated addition to emulate multiplication, right? And if I want to multiply, let's say multiply let's say x into y, right? It is something like adding x y times, right? So you can initialize something like some sum could be 0, and you want to do sum plus equal to plus equal to x, and this has to be repeated y times, then the result will be x into y. How will you do this? This can only be done if you have a loop that could be controlled and you want to specifically execute this loop y times. So for that, this JNZ would be very helpful. If you do not have that, this is going to keep on happening, and you will get the entire multiplication table for x. Right? You get x, you get 2x, 3x, 4x, 5x, 6x, dot dot dot, up to the time your registers do not overflow. Right? So you can have this controlled loops by using this conditional chumps. Okay, so next we are going to look into a few sample programs that are implemented using our instruction sets, right? And we have to also define our instruction format, right? So we have to give some identity to each one of these instructions, because we are based on these definitions we are going to define the rest of our computer, right? So you have to say that, okay, LDA, what is your opcode, what is the opcode for LDI, what's the opcode for ST, and so on. Once you fix that, then only you can design the rest of the circuit, because we want to make something very very concrete, right? I understand that you can assign some arbitrary value to them and get it working. Again, we are also going to do the same. I'm not saying that the opcodes are going to be motivated by some optimization aspects or something which makes the hardware implementation easy. We are not going to go into those kind of details. We are going to just assign some opcodes, but the point is that we have to assign them and not keep it abstract, right? We have to actually assign opcodes to this individual instructions and get started with the actual designing of the microarchitecture. Okay,